If you have any questions, unmute yourself during the talk and you can ask the speaker. Today we have Andy Zhang from the University of California, Berkeley campus, and he'll be speaking on filtering Grassmannian cohomology via k-Schur functions.
Okay, thank you for the invitation. This joint work with my collaborators is about filtering Grassmannian cohomology via k-Schur functions. And in the meantime, Huda will take questions in the chat from the audience. I should say in the beginning that this talk will be centered around a conjecture in algebraic combinatorics called the Reiner and Tudose conjecture, or simply we denote it by the R-T conjecture, which has been an open problem since 2003. Before introducing the conjecture, we shall briefly discuss some preliminary definitions and theorems. Then we'll state the R-T conjecture and present the way to visualize it, and then try to comment on some boundary cases that we know is true. We shall see that there is a very natural combinatorial interpretation via k-conjugation, and which lead to a conjectural basis that will prove the R-T conjecture. And finally, we'll make some comment on some generalization of the R-T conjecture in different Lie types. In particular, there is an analog of the R-T conjecture in type C, namely the conjecture for the Lagrangian Grassmannians. So let's start off by reviewing some symmetric function theory. So we call a partition k-bounded if its first part, lambda1, is at most k. And we denote the set of all k-bounded partition by this notation pk. And in this talk, I'll refer to a lot about this ring lambda k, which is the k-bounded symmetric function ring. It's defined by adjoining k variables to q. And we call these variables h1 through hk. And you could think of them as the complete homogeneous symmetric functions. And alternatively, this ring is also generated by e1 through ek, the elementary symmetric functions. So as we know from symmetric function theory, and these polynomials h1 through hk are algebraically independent. So we could describe its additive basis by using the set pk. And concretely, it has basis of h lambdas, where lambda is taken from pk. Or alternatively, another basis is obtained by taking all e lambdas, where lambda is taken from pk. So now we can introduce the main object of our interest, which is the cohomology ring of the complex Grassmannian with rational coefficients. And we shall denote that by this RLK. And the following theorems gives a very nice and concrete presentation of this ring in terms of generators and relations. As you can see, there are two different ways to present this ring, and we shall focus on the second way to present it in this talk. It's obtained as a quotient ring of this lambda k, q adjoint h1 through hk, by quotienting out some polynomials in terms of h1 through hk. And these polynomials are given exactly by the determinant of this I by I matrix. And these are called the Jacobi-Trudi determinants in the literature. We shall also note that this ring is graded, meaning that it can be decomposed as a direct sum of various graded pieces. And we set the degree of EI or HI to be I. Recall that for any graded algebra, or graded vector space R over a field, say Q, we can define its Hilbert series by just taking the generating functions of the dimension of each graded piece. And in particular, we're interested in studying the Hilbert series of this ring RLK, the cohomology ring of complex Grassmannian. And before we state this theorem, let's define what a Q analog of a positive integer is. A Q analog of a positive integer n is defined to be the polynomial 1 plus q plus dot 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 plus q to the n minus 1. So in particular, if you set q equal to 1, then the right-hand side will become just n, the ordinary positive integer. And similarly, we could define the factorial, we could define the q analog of the factorial. It's just what you expected. You're taking the q analog of n and n minus 1 and dot 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 and 1, and you take all their product. And then we can define what the q binomial coefficients are. These are defined similarly to the ordinary binomial coefficients, where instead of factorial, you just take q analog of factorials. So in this expression, if you just set q equal to 1, then this expression just becomes the ordinary binomial coefficient formula. Another way to think of it is to think of it in terms of counting partitions inside its L by K ambient rectangle. So, so this leads us to this theorem. Because we can decompose the Grassmannian into Schubert cells indexed by partitions lambda inside this L by K ambient rectangle, we have a CW decomposition, and consequently, this Hilbert series of the cohomology of Grassmannian is just the Q binomial coefficient. So we are interested in studying a very natural family of the subalgebras generated by the first m variables, h1 through hm. In particular, we get a filtration of the ring RLK. So the subalgebra RLK0 is just the base field Q, and the subalgebra RLK1 contains the subalgebra RLK0, and so on. So Reiner and Tudose in 2003 have come up with a conjecture stating what the Hilbert series of the M subalgebra is. It is this complicated Q binomial coefficients with double sums. It's very difficult to get familiar with this this complicated binomial coefficients expression. So we could simplify it by stating it in another form. Well, you can take this difference between the consecutive Hilbert series, and this allows us to remove one of the double sum, but it still looks very complicated. And so let me try to make a visualization of this conjecture. So here is a picture of the Hilbert series of the ring R66. On the x-axis is the degree of the graded pieces. So it ranges from 0 to 36, because the dimension of the Grassmannian GR612 is 6 times 12 minus 6, which is 36. And I use various colors to denote the subalgebras of this this ring R66. And on the y-axis, you have the dimension of each graded piece. or equivalently, it is the coefficient in the Hilbert theory. So for example, the ring R660 is just 1, where you just have this, this one box down here. And the ring R661 is represented by this, this red region. And you can read it as 1 plus q squared plus q cubed all the way to q to the 36. And if you take m to be 6, which is the maximal possible value, you would get the entire bar graph, which is just R66. Another way to interpret this bell curve shape is just to read the height as number of ways to make partitions of size d inside the ambient rectangle. For example, in degree 18, I think this height is 58. This means that we can, there are exactly 58 ways to partition 18 inside a 6 by 6 rectangle. And that also explains why this graph is symmetrical. Okay. So the R-T conjecture is known to be true in the edge cases. In the simplest cases, we can take m to be 1. And this conjecture will reduce to the statement that the Hilbert theory of RLK1 is just 1 plus q plus dot 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 plus q to the k times L. So the maximal dimension is k times L. This can be deduced from either Schubert calculus or using the Hart-Lefschetz theorem from algebraic geometry. And in the other extreme, we can take m to be as large as possible. So we can take m to be the minimum of k and L. And the conjecture must be consistent with the theorem that the entire graded algebras Hilbert theory is the Q binomial coefficients here. So more concretely, if we go back to the conjecture and say, without loss of generality, let's assume k is less than or equal to L. So if we plug in k inside M, then the right-hand side should reduce to the binomial, the Q binomial coefficients, k plus L to L. And this is not obvious. Actually, it's a statement in combinatorics that's that leads to some insight of this this conjecture. So in order to explain the first combinatorial interpretation of this R-T conjecture, we shall define some notions. We say a k-bounded partition lambda is I vacant if I is the largest integer for which the you can fit in a I by I minus 1 rectangle in the complementary skew diagram. So here we have a 5-bounded partition lambda 4, 4, 3, 3, 1. And this fits inside the rectangle 5 by 5. And it's 3 vacant because if you look at the complementary skew diagram, you can fit inside a 3 by 2 rectangle, but not a 4 by 3 rectangle. And 3 is the largest number for which I times I minus 1 rectangle can be fitted inside the complementary diagram. So this definition may not seem to be natural at first glance, but please allow me to explain it in the next slide. If we observe the conjecture closer enough, we can see that the right-hand side of the expression can be broken down into 4 different parts. And I labeled them with different colors down here. So a very useful property of I-vacant partition is that you could divide it up into 4 different pieces. If we know that this partition is I-vacant, then we know for sure that the blue region is filled completely, and so is the red region. But however, we're not sure about the yellow region or the green regions. There could be any partition that fit inside the ambient rectangle. And that's why we have the Q binomial coefficients here. So this says that for each partition, there's exactly a number I such that the partition is I-vacant. And then we can decompose it according to these 4 portions, and they correspond to expressions inside the right-hand side of the R-T conjecture. So to formulate it in another way, it's saying that the right-hand side of the R-T conjecture is the same as a generating function counting all I-vacant partition where I is at most M. And in the second form, if we consider the quotient of the subalgebras, it's just counting the M vacant partitions. Well, this seems very promising, but one drawback of this is that for M vacant partition, there's no nice algebraic object that's associated to it. So we'll push it further by considering a technique called k-conjugation, which will see that it leads naturally to a nice basis. Before introducing the technique of k-conjugation, let's recall that the k-bounded partition is just a partition where the first part is at most k. And we also recall that the hook length of a box B in the Ferris diagram or Young diagram of a partition lambda is the number of boxes weakly to the right and weakly below B. So in the example here, we have the 4-bounded partition 4311. And if we look at this box, its hook length is 7 because there are 3 boxes to the right and 3 boxes below it. And if you also count itself, then you'll get 7 boxes. Another useful definition is the so-called k+1 core. The definition is very simple. It's just a partition where no box has hook length equal to k+1. You may wonder that why shouldn't we define k core instead of k+1 core? That's because it's very convenient for the following theorem. I claim that there actually exists a bijection between k-bounded partition and k+1 core. And it's a very natural partition. I will illustrate it by showing 2 examples. So if you start with the 4-bounded partition lambda, the same example I used previously, 4311, then we're trying to turn it into 5 core. A 5 core means that it has no box with hook length that is 5. So we just look at it from bottom to top. And so the algorithm goes like this. If you see a hook length that is greater than or equal to k, then you just slide the entire row to the right. And by doing so, you may introduce new boxes, but that's okay, because the introduced new boxes will have hook lengths greater than k+1. So in this example, the fourth bounded partition 4311 will be turned into a 5-core 8411. And here's another example. If we start out with a 4-bounded partition 221, it will be turned into a 5-core 321. And conversely, you just remove all the boxes that has Cook length greater than or equal to k+1 inside a k+1 core. And then you shift all the remaining boxes to the left, and you will get the original k-bounded partition. So the map C stands for core, and the map P stands for partition, and they're inverses to each other. So why am I introducing the C and P? Because that's what we needed to define the so-called K conjugation. Recall that the ordinary conjugation is just to flip the partition across its diagonal, but we couldn't do that for K-bounded partition, because in doing so, we would not necessarily obtain another K-bounded partition. So if we first turn it into a K+1 core, and then do the usual conjugation, and then we apply the inverse map, we'll guarantee to have a K-bounded partition as the K conjugate. So this is very useful because it's an analog of conjugation in the K-bounded partitions. So here we start with the 4311 4-bounded partition. And then as we've seen in the previous slide, it's turned into a 5-core 8411. And then by doing the usual conjugation, we get 4221111, which is also a 5-core. And finally, we apply the inverse map by removing the gray boxes and sliding everything to the left. And we'll get another 4-bounded partition, 2111111. And these are described in by Lapointe, Lascaux, and Morse in their 2003 paper. So let's view it in a larger scale. If we take all partitions that fit inside the 3x3 rectangle, and we do the 3 conjugation for all of them, we'll get the following partitions. And the way I colored them is because of the following reason. Down here, the red partitions are 1-bounded partition. The blue partitions are 2-bounded but not 1-bounded partitions. And the green one is 3-bounded but not 2-bounded partition. And up here, it's actually difficult to see, but these red partitions are 1 vacant, and these blue partitions are 2 vacant, and this green partition is 3 vacant. So this suggests that a K-bounded partition lambda is M vacant if and only if its K conjugation has its first part equal to M. And is this a general phenomenon, or is it a coincidence? It turns out that this is actually true in general. If we begin with a K-bounded partition lambda that is I vacant, then its K conjugation has the first part exactly M, exactly I, and vice versa. So from now on, we shall denote the set of partition whose K conjugate fits inside the L by K rectangle to be the set PLK. And we can further refine it by taking the subset of it that has the first part at most M. And we shall denote that by PLKM. So this is a subset of PLK. in particular, if we take M to be the minimum of K and L, this just reduces to PLK. So to restate the theorem, a K-bounded partition lambda is I vacant for some I less than or equal to M, if and only if its K conjugate is inside PLKM. And a partition is M vacant if and only if its K conjugate is inside the set PLKM, but not in PLKM minus 1. So this is just a restatement of the theorem here. Sorry. So to put it together, in Reiner and Tudose's paper in 2003, they implicitly stated that the conjecture counts the number of counts the partition that are I vacant and where I is at most M. And we've shown that we can reformulate this to be a generating function where lambda is taken from PLKM, which is the K-bounded partition whose K conjugate is inside the K by L rectangle and whose first part is at most M. Equivalently, for the second form of the Reiner-Tudose conjecture, this is stating that if we, this expression is just counting the partition inside this complement. I think this interpretation is better than the previous one because it relates to some algebraic object, which we'll discuss briefly now. Oh, and before we do that, let's pause for a while and look at what this implies in terms of the Reiner-Tudose conjecture. We know that the Hilbert theory of the zero subalgebra is just 1. And the Hilbert theory of the first quotient is this q plus q squared plus dot 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 plus q to the 9th. And so on and so forth. And it's not difficult to see that there's an obvious connection between these. But it's actually still a conjecture that these relations remain true in general. So equivalently, we could state the R-T conjecture in terms of a very explicit formulation of basis. So the R-T conjecture is equivalent to the statement that there exists some set F lambda where you use PLK as the index set with the 3 extra properties. So the first property is that for each lambda, F lambda should lie inside the subalgebra RLK lambda 1. So so this is saying that it should behave well with respect to the basis, with respect to the filtration. The second property says that this is an additive Q basis for RLK. And the third property says that if we further refine it, we shall have the property that if we start out with a partition inside PLKM, then F lambda should be the set of F lambda should be a Q basis for RLKM. And I should comment that the property C actually imply property B by just taking M to be maximal. Okay, so as we have seen in the previous example, the formula appeared in the R-T conjecture is the formula counting partitions inside the index set PLK. So it's very natural to ask whether there is some algebraic object that represents this combinatorial object. This leads us to introduce the so-called k-Schur functions. And traditionally, the Schur functions in Schubert calculus was defined to be defined by inverting the unitriangular system in the symmetric function ring lambda, where you take the coefficients to be the so-called constant numbers. And here we define the k-Schur function similarly, just by replacing the constant number by the k constant numbers. These k constant numbers are defined as the number of k-tableaux of shape C of mu and k weight lambda. I should not go into detail what this terminology means. But the key point here is that this formulates a k version of Schubert calculus. So actually, I have put a slide about the definition of k-tableaux and k weight. So recall traditionally, we have the constant numbers are defined to be a number of Young tableaux of some certain shape with certain weight. And here, we just define a notion of k-tableaux similar to the traditional notion. It's defined to be a tableau of shape C of lambda, and you also specify some weight, which you will use later. And these tableaus should satisfy the two additional properties, that rows are weakly increasing and columns are strictly increasing. And the second property says that you should limit your attention to the tableaus with the property that they're exactly k+1, they're exactly mu I distinct k+1 residues. But I won't introduce the notion of residue here. So for example, the three tableau of three weight 1, 3, 1, 2, 1, 1 and shape 8, 5, 2, 1 are the following three tableaus. I think the main takeaway here is that this definition allows us to formulate a analogous version of Schubert calculus in the setting of k-bounded partition. And in particular, we could ask how these k-Schur function behave under the notion of conjugation. So let's recall that the k-bounded symmetric function ring lambda k has a natural algebra involution omega that takes E lambda to H lambda. So this induces an algebra involution on the quotients, which we also denote as omega. And these two involutions are related in this commutative diagram. And you can check the commutativity by just tracing the generators H1 through HK here and see where the maps send the generators to in the destination. And we also note that RLK is isomorphic to RKL. That's because the Grassmannian k plus L is isomorphic to the is homeomorphic to the Grassmannian L k plus L. So these k-Schur functions enjoy the properties that they form a basis of RLK. So if we ask what the involution do on the k-Schur functions, Well, the answer is very simple. The involution takes a k-Schur function to another k-Schur function, but you also need a change of index, and the change of index is precisely described by this k conjugation. So, combining this theorem and the previous one, we arrive at the conclusion that the set of k-Schur functions whose index k conjugation is inside the L by k rectangle forms the basis of RKL. And recall that we denote this index set by just PLK and PLKM respectively. So this corollary just says that we could use the k-Schur functions with the index set PKL as a basis of RLK. This all seems pretty promising because you have a basis that uses PKL as an index set, but it's not that simple because it doesn't behave well with respect to the filtration, meaning that if you start out with a partition lambda, which is m-bounded, the k-Schur function indexed by lambda is not necessarily inside the M subalgebra. So to fix this, it's necessary to look at some other set of bases with the index sets PKL and PKLM. So the first basis we're looking at is the complete symmetric function basis. This enjoys the property that if you start with a m-bounded partition lambda, H lambda will be inside the subalgebra RLKM. And second of all, we could also look at the k-Schur functions, but this time without a fixed k, but a varying I, which is just the first part of the partition we are looking at. So the k-Schur functions, the I-Schur function will depend on the partition. And this also enjoys the property that if you start with a partition lambda, which is m-bounded, the element it's indexing will be inside the M subalgebra. So these two conjectures are separate, but equally powerful. Part B of either conjecture will imply the full R-T conjecture because of our new combinatorial interpretation. And part A of either conjecture is still strong enough to show half of the R-T conjecture because it sets an upper bound on the expression of the R-T conjecture. So I should comment that this is sufficient to greatly simplify the proof of Hoffman theorem, which is what Reiner and Tudose originally tried to do. And what is the Hoffman theorem? It's a statement that that characterizes the endomorphism ring of RLK. And the original argument depends on very heavy machinery from algebraic geometry, like the Hart-Lefschetz theorem and some other things. By characterizing the Hilbert series of each subalgebra of the cohomology ring, Reiner and Tudose was able to deduce the Hoffman theorems very easily. And we refer the interested reader to Reiner and Tudose's original paper. Okay, another direction we took in our research was to find different analogs for the R-T conjecture. And before introducing this analog, we shall introduce some notions. So if we focus our attention instead on this strictly decreasing partition, or the partition with distinct parts, we could define its shifted Young diagram to be a diagram with boxes aligned in a triangular fashion. And similarly, we could define an ambient triangle of size n, denoted as delta n. This is just a shifted Young diagram n minus 1 all the way to 1. So in this example, we're looking at the ambient triangle delta 5 and the shifted Young diagram 5, 2, 1. So why is this relevant? The type C analog of the complex Grassmannian is the so-called Lagrangian Grassmannian. Recall that the complex Grassmannian can be described as a parametrizing space of all k-planes in n-dimensional complex vector space. And the Lagrangian Grassmannian is a parameter space for the maximal isotropic subspaces inside a symplectic vector space. And we denote that by Lg of n to n. And we could study its graded, we could study its Hilbert series. So before doing that, I should mention that Borel also have this nice presentation of the ring in terms of generator and the relations. It's generated by n variables with certain quotients. But the Hilbert series turns out to be very simple. It just counts the shifted partition, the partition with distinct parts inside the size n ambient triangle. And more concretely, this is the product of 1 plus q to the I, where I ranges from 1 to n. And in our research, we observed that there's an analog for the R-T conjecture. If we look at the subalgebra generated by E1 through EM, we could define Rnm sub-Lg. And the Hilbert series of this turns out to be this rather complicated Q-binomial coefficients. And notice the similarity between this expression and the original R-T conjecture. This suggests that we could divide each partition in terms of their I vacancy. And in fact, there is a notion of I vacancy in this case. However, it still remains a mystery that how the discussion of k-Schur functions and k-conjugation can be applied here. And I think that will be a very exciting direction for future research. And that concludes my my talk on the recent progress of the R-T conjecture. Thank you all for listening.
Thank you. Anybody has any questions? So looks like maybe there are no questions. So let's.
Yeah, I have one. So
Okay.
might be a sort of very simple question, but can you go back to the figure that you drawn, Andy? So I see through the figure that
Which one? The bar graph?
the first figure, yeah, the diagram
Yes.
that you drew for the constants, yeah, yeah.
Yeah.
So it's sort of at a certain stage everything coincides with the previous graph. Is it just a coincidence with the R66 or is a general phenomenon that's hiding here?
I think this graph is very interesting. You can read off a lot of information just by looking at this graph, right? So for example, this looks like a bell curve shape, right? This is because so first of all, it's symmetrical because if you start with a partition, you can take its complement. So if you start with degree D, then there will be a complement of it inside the K by L rectangle in dimension K times L minus D. And then this is unimodal because unimodality means that there's only the curve is first increasing then decreasing. And there's a unique maximal here because this is guaranteed by the Hard-Lefschetz theorem, where it states that there exists isomorphism between degree D and the degree K times L minus D. And this isomorphism is given by multiplying some power of the hyperplane class. And so this will guarantee that there's only one unique maximal. And
yeah, when you focus on the third part, R663 maybe, the third one. So
third one?
above, yeah, this one. So there are two maximums for this. Is it?
Where are the maximum?
Yeah, these two.
Oh, here, like
yeah, equal. So it's a sort of weak unimodular or.
Well, this also satisfies unimodality because by unique maximum, I mean that you can there's a point where everything starts to decrease, and up until that point, everything is increasing.
No, thought as a sequence of the coefficients, they are unimodular. You said, but sort of.
Well, we don't know anything about the unimodality of the subalgebra, but we know for sure that the bell curve is unimodal. Yeah, we still couldn't prove that the subalgebras have the property of unimodality.
Okay, thank you.
Yeah.
Yeah. Is there any other question? Okay, so can we all unmute ourselves and thank the speaker? Thank you, Andy, for this talk.
Thank you.
So the slides of this talk are already available on our webpage, and Huda has also shared the archive link in the chat box if anybody wants to go and see that. And yeah, so this is the last talk for this current semester, and we'll meet soon after the winter break. Okay, thank you for joining us.